Hello students, happy morning. Class 12 physics. From today onwards, let's start our revision class for unit 3, that is magnetism and the magnetic effect of electric current. Let's start our revision by go through the book back question. Okay, our first subtopic, that is introduction to magnetism. Our first question, that is a very short answer question. What is meant by magnetic induction? Magnetic induction, that is the process of magnetize the magnetic substance, okay, by means of magnet or magnetic material. Okay, see, magnetic induction is a process by which the magnetic substance is magnetized under the influence of magnet, and also it can be stated as magnetic flux. Okay, number of magnetic field lines crossing through a given area, and also it can be stated it as total magnetic field. See, the magnetic induction or total magnetic field. Okay, to answer the question, you have to know this equation. B vector is equal to B naught vector plus Bm vector. Here B vector is a total magnetic field. B naught is a magnetic field in the vacuum. Okay, and Bm is a magnetic field in the medium. We know B naught is a magnetic field in the vacuum, that is due to the magnetizing field, and Bm is a magnetic field that is due to the induced magnetization of the substance. Okay, we can state this one as the magnetic induction or total magnetic field inside the specimen is equal to sum of the magnetic field B naught produced in the vacuum due to the magnetizing field, and Bm, okay, that is magnetic field in the medium due to the induced magnetization of the substance. Okay, then our next question, what is magnetic flux? Okay, magnetic flux, the number of magnetic field lines crossing any given area that is normal to the surface. Okay, the number of magnetic field lines crossing any given area normally is defined as a magnetic flux. Okay, that is same as that of electric flux. In electric flux we are considering the electric field line. Here it is a magnetic field line. So the magnetic flux is defined by the symbol, that is phi b is equal to b vector dot dA vector. Here it is a dot product of two vectors, so phi b is a scalar. Okay, dot product can be represented as BA cos theta. Okay, the unit of flux is Weber and the dimension is m L square T power minus 2 A power minus 1. Here A is a ampere. Okay, we already discussed this. Then define the magnetic dipole moment. Okay, dipole moment, we know dipole. Okay, that is here magnetic dipole, so we can consider two poles are separated by a small distance. Okay, that is known as magnetic dipole. Here it is, the question is define magnetic dipole moment. Okay, for this we need to know the formula, that is Pm is equal to 2L into Qm. Okay, see, to answer the question you have to know this relation, Pm is equal to Qml. Okay, Qm is the pole strength of the magnet and 2L is the distance between the two poles. Okay, see, magnetic dipole moment, the product of pole strength and the magnetic length of the bar magnet is called magnetic dipole moment. Product, that means multiplication of pole strength, that is Qm, and magnetic length, that is 2L, that is known as magnetic dipole moment. Okay, see, here it is a which quantity? It is a vector quantity that is denoted by the symbol Pm vector. We can write Pm vector is equal to Qm into D. Okay, that is D vector. Qm is a pole strength and D vector is a vector that drawn from south pole to north pole. In electric dipole moment, that is from negative charge to positive charge. In magnetic dipole, that is the dipole moment direction is from south pole to north pole. Okay, D vector modulus, that is equal to 2L, that is known as magnetic length. Okay, we can write Pm is equal to 2Qml. Then the unit, that is SI unit of magnetic pole strength, magnetic moment is ampere meter square, and its direction is from south pole to north pole. Okay, then our next question, define magnetic declination and inclination. Okay, magnetic declination. Okay, if suppose if we place a bar magnet, that means if we suspend a bar magnet it does not exactly align with the geographic poles. Okay, it align with the, it creates some angle with the geographical axis. Okay, that means the angle between the magnetic meridian at any point and the geographic meridian, that is called magnetic declination. Okay, if suppose I suspend a bar magnet, okay, it will come to rest in a direction. That direction is not exactly in the direction of the geographical axis. Okay, it creates some axis. That axis is known as magnetic axis, that is known as magnetic meridian. The angle between the magnetic meridian and the geographic meridian is known as magnetic declination. Okay, at a higher altitude it will be greater declination, at the equator it will be small. Then magnetic inclination, the angle suspended by the earth total magnetic field with the horizontal direction of magnetic meridian is known as dip or magnetic inclination. See, the angle between the earth total magnetic field with the horizontal direction in the magnetic meridian, it is an angle between the horizontal component of earth magnetic field and the total magnetic field, that is known as angle of inclination. Okay, then our next question, discuss the earth magnetic field in detail. Okay, first of all, William Gilbert, he proposed the earth behave like a gigawatt powerful magnet. Okay, this is due to the temperature inside the earth is very high. Okay, this is the reason behind the Gilbert proposed. Okay, but that much of temperature is not possible inside the earth. Okay, due to that temperature it does not retain the magnetism. Okay, magnetism will be affected due to the temperature. Then Gower, he suggests that the earth magnetic field is due to the hot rays coming from the sun. Okay, due to this earth behave like a magnet. Okay, in order to understand the earth magnetic field, we need to know the three parts. Okay, we need to study geomagnetism. To understand this, we need to know three parts, that are magnetic declination, magnetic inclination, and horizontal component of earth magnetic field. First of all, magnetic declination we know very well, that is an angle between magnetic meridian at a point and the geographic meridian, that is denoted by the symbol D. Okay, then magnetic dip or inclination, that is an angle suspended by the total earth magnetic field with the horizontal direction in the magnetic meridian, that is denoted by symbol I. Then horizontal component of earth magnetic field, that is a component of earth magnetic field along the horizontal direction. Okay, here the earth total magnetic field at all the point, that will be split up into two components, that is horizontal and vertical component. The component that is parallel to the surface of the earth, that is known as horizontal component of earth magnetic field. Okay, here BE, it is a earth total magnetic field, and BH horizontal component, and BV vertical component. The horizontal component can be represented as BH is equal to BE cos I. I is the angle of inclination. Okay, then vertical component, that is denoted by BV is equal to BE sin I. Okay, then dividing these two, then we get tan I is equal to BV by BH. At the equator, okay, at the equator, the angle between the magnetic field and the surface is parallel, so angle of inclination is 0, so we can write BH is equal to BE. At the equator, the horizontal component of earth magnetic field will be maximum. Okay, angle of inclination will be 0 and the vertical component of magnetic field will be 0. At pole, the angle between the total magnetic field and the surface will be 90 degree. Okay, so we can write theta is equal to 90 degree, that means I is equal to 90 degree. Horizontal component of earth magnetic field will be 0 and vertical component of magnetic field will be maximum. Okay, then our next topic, Coulomb inverse square law of magnetism. Okay, we already studied in our electrostatics, Coulomb inverse square law in electrostatics. Okay, on that Coulomb state that there is a force of attraction or repulsion between the 2 point charges. Here also a force of attraction or repulsion between the two magnetic poles. Okay, see, state Coulomb inverse law in magnetism. The force of attraction or repulsion between the two magnetic pole is directly proportional to the product of their pole strength. Okay, and inversely proportional to the square of the distance between the two poles. If the pole strength increases, force between the two poles increases. It may be attractive or repulsive. Okay, then the distance increases, the force will less. Okay, our next topic, by using the Coulomb's law, that is Coulomb inverse square law, we can find the magnetic field at a point along the axial line of a magnetic dipole, that means bar magnet. Okay, we already discussed this topic in first unit. On that we already found the electric field at a point along the axial line of a electric dipole. Okay, here we find the magnetic field due to a magnetic dipole, that means we need a bar magnet. Okay, so far here I am considering a bar magnet. Okay, here see, I consider a bar magnet having south and north pole, having the same pole strength. From the center O, at a distance of R, okay, I locate a point C in its axial line. Okay, we need to find the magnetic field at the point C. Okay, so far here I am considering a unit north pole having the pole strength 1 ampere meter, unit north pole. Okay, so this north pole will repel this north pole. Okay, so the force of repulsion is in this direction. Then this north pole will be attracted by this south pole. Okay, so the force of repulsion in this direction. Okay, this north pole and the unit north pole are in the distance of r minus L. Okay, and this south pole and this north pole at a distance of r plus L. Okay, we know this is a magnetic pole, so having the pole strength Qm and Qm, okay, having the same pole strength at a distance of separation, that is 2L. Okay, we need to find what? Magnetic field. Okay, we know magnetic field is a force experienced by the unit pole. Okay, magnetic field is a force experienced by the unit pole. We know force can be written as F is equal to mu naught by 4 pi Qm by r square. Okay, here Qm is pole strength of this north pole, and one more Qm is pole strength of this unit north pole. That is, unit means we can represent it as 1 ampere meter. Then divide by that same, we can get magnetic field. Okay, magnetic field is a force experienced by the unit pole. Okay, then the magnetic field at the C due to the north pole, magnetic field at the C due to this north pole can be written as Bn vector is equal to mu naught by 4 pi Qm by r minus L. There is a distance between the north pole and the unit north pole. Okay, so we can write this I cap is a unit vector, it denote the direction of the magnetic field. Okay, then the magnetic field at C due to the south pole. Okay, here this south pole and this north pole are at a distance of r plus L. Okay, but this force experienced by this south pole is in the direction opposite to the direction of this north pole. Okay, so the magnetic field also in the same direction, that is in negative x axis. Okay, so we can write minus. Then the total magnetic field at the point C due to the magnetic dipole can be written as B vector is equal to Bn vector plus Bs vector. Okay, this is a magnetic field due to the north pole of the dipole. Bs is a magnetic field due to the south pole of the dipole. Okay, then substituting these two expression in this one, then we get B vector is equal to this one. Okay, on simplifying this, we get B vector is equal to mu naught 2r by 4r. Okay, then we get Qm into 2L. We know Qm into 2L is known as dipole moment, that is Pm. Okay, then we can write Pm. If suppose the point C is taken far away from this magnetic dipole, okay, so we can write R is greater than L, so we can neglect L from this expression. Okay, so we can consider B axial, that is equal to mu naught by 4 pi 2 Pm by R cube. Okay, because it is R power 4, then R cancel, then we get R cube. Okay, the net magnetic field due to the magnetic dipole on its axial line is in the direction of positive x-axis, okay, is in the direction of the magnetic moment. Okay, we know magnetic moment is from south pole to north pole. At the same direction the magnetic field will be there. Okay, then we can write pm into I cap, that can be written as pm vector. Okay, we get b axial is equal to mu naught by 4 pi 2 pm vector by r cube. Okay, then our next topic, that is magnetic field at a point along the equatorial line due to a magnetic dipole. Okay, for this question we need to consider a magnetic dipole. Okay, having the same pole strength qm, here it is south pole, it is north pole, the magnetic moment is from south pole to north pole. It is a geometrical center of the magnet. Okay, from that point O at a distance r, we are considering the point C. We need to find the magnetic field at the point C alone. So we are applying the Coulomb inverse law. Okay, we know Coulomb inverse law, that is F is proportional to qm by r square. Then after, by using that we can find magnetic field, that is magnetic field is a force experienced by the unit pole. So for the simplicity we are considering the monopole. Okay, that is the north pole having the pole strength qm we are placing here. Okay, then this north pole experience a repulsive force due to this north pole, then it will move in this direction, then the magnetic field is in this direction alone. Okay, then this north pole experiencing the attractive force this due to the south pole, then it will move towards this direction. Okay, here this magnetic field and this magnetic field are in xy plane. Okay, so it can be split up into two components, that is see bn vector is split up as bn sin theta and bn cos theta. Okay, then bs can be split up into bs cos theta and bs sin theta. Okay, here it is in positive y-axis, so j cap. Here it is in negative x-axis, so I cap. Okay, here also it is in negative y-axis, that is j cap. It is in negative x-axis. These two components, that is vertical component bn sin theta I cap, bs sin theta minus j cap. Okay, this is j cap. These two are equal and opposite, so they are nullify each other. Okay, then the net magnetic field can be represented as the magnetic field at the point C, that is b. See, the total magnetic field, that is b vector is equal to bn vector plus bs vector. Okay, we know this bn is split up into two components, that is bn sin theta and bn cos theta. This bs also split up into two components, that is bs cos theta and bs sin theta. These two are equal and opposite, so they are cancel each other. So we can consider this component alone. Okay, that is the horizontal component alone we can consider. So we can write b vector is equal to, see, these two are in negative x-axis. Okay, negative x, so we can write minus bn cos theta I cap minus bs cos theta I cap. Okay, see, here cos theta is common, we are taking out of the bracket. Okay, then we know this point C is at equidistance from the north pole and the south pole. So the magnetic field at the point C having the same magnitude. Okay, so we can write, that is bn is equal to bs. We know magnetic field between the magnetic field due to a point charge. Okay, that is point monopole, magnetic field due to a monopole, that is bs is equal to mu naught qm by 4 pi. Here the distance is r dash. Okay, here also it is r dash. R dash is equal to, by using Pythagoras theorem we can write r square plus l square square root. Okay, square root of r square plus l square. Okay, so we wrote this, then we substitute the value of r dash, we get r square plus l square. Okay, then cos theta can be considered as adjacent side by hypotenuse, that is l by root of r square plus l square. Okay, substituting this we get this. Then the magnetic field at the point C we are considering, so if suppose we are considering the magnetic field at the point C from that is far away from the dipole. Okay, so far we are neglecting the value of L. Okay, if suppose the point C is taken far away from the magnetic dipole, so we are cancelling the value of L because R is greater than L. Okay, see, we are cancelling the value of L, then we get R cube. On modifying this, we get B equatorial is equal to minus mu naught by 4 pi Pm by R cube into I cap. Okay, then Pm into I cap, that is we know Pm vector. Here the magnetic field at the equatorial line due to a bar magnet, that is in the direction opposite to the direction of the magnetic dipole moment. Okay, see, minus mu naught Pm by 4 pi R cube. Okay, see, the magnetic field due to a bar magnet in its axial line, that is in the same direction of magnetic dipole moment, but for the equatorial line the magnetic field is in the direction opposite to the direction of magnetic dipole moment. Okay, then our next question, that is, this is a subtopic, that is torque acting on a bar magnet in uniform magnetic field. Okay, the question is compute the torque experienced by the magnetic needle in a uniform magnetic field. Okay, this is a question we already discussed in first unit. Okay, on that we are finding the torque experienced by the electric dipole in its uniform electric field. Okay, here we need to find the torque experienced by the magnetic needle, that means magnetic dipole in a uniform magnetic field. So far I am considering a magnetic needle, that means a bar magnet having the length 2L and pole strength is Qm. Okay, that is placed in a uniform magnetic field. This is a uniform magnetic field. I am placed with the bar magnet. Okay, here this north pole experiences a force in this direction and this south pole experiences a force in this direction. Okay, here it is a direction of dipole moment. Okay, due to these two equal and opposite force, the net force on the magnetic magnetic dipole will be 0. Okay, so it form a couple which tend to rotate the magnetic dipole in a clockwise direction. Okay, that constitute a torque. The torque can be represented tau vector is equal to On vector cross Fn vector plus Os vector cross Fs vector. Okay, here On vector from the midpoint of the, that is a geometrical center of the magnetic dipole to the north pole. Okay, and Os vector, that is a unit vector from point O to, that is S. Okay, on substituting this, then we get this one. Okay, here in order to find the magnitude, we can write this one as tau is equal to, okay, On vector modulus dot, that is Qm B vector modulus sin theta. Okay, this one became Os vector modulus, then minus Qm B vector modulus. Okay, then sin theta. Then after substituting, then we get tau is equal to L Qm B sin theta, L Qm B sin theta. Okay, on solving this, we get tau is equal to 2L Qm B sin theta. 2L Qm, that is a magnetic moment. Okay, so we can write tau is equal to Pm B sin theta. Then Qm into 2L is equal to Pm, we substitute here. Then in order to write in a vector form, we can write sin theta as cross product of two vector. Okay, then tau vector is equal to Pm cross B vector. If suppose theta is equal to 90 degree, it attain maximum torque. After attaining this torque, it will align the direction of the uniform magnetic field. After attaining that position, the net torque on the dipole will be 0. Okay, then our next topic, that is magnetic properties. Okay, this we already discussed. This is also a magnetic property. Then our next property, what is magnetic susceptibility? To answer the question, you have to know this is the expression chi m is equal to m vector modulus by h vector modulus. Here chi m is a susceptibility and m vector, that is the intensity of magnetization. Okay, and H vector, it is a magnetizing field. We can write this one as the magnetic susceptibility is a ratio of intensity of magnetization induced in the material due to the magnetizing field. Okay, here it is a dimensionless quantity. Then magnetic permeability. Magnetic permeability, you know already, that is electric permeability. That means the ability of the material to allow the passage of electric field lines. Here magnetic permeability, it is the ability of the material to allow the passage of magnetic field line. Okay, it's having the unit Henry meter power minus 1. Okay, then our next question is from classification of magnetic material. Okay, see what happened to the domain in the ferromagnetic material in the presence of external magnetic field. Okay, if suppose a ferromagnetic material is placed in a external magnetic field, what happened to the domain? Two things will happen. Okay, first one, the domains having the magnetic moment that are parallel to the field that grow in size. Okay, what are the domains that are parallel to the magnetic field that will grow up in size? Okay, then other domains that are not parallel, that will rotate and align with the direction of the magnetic field. Okay, two things happened. One is the domain that are parallel to the magnetic field that will grow up in size, and the other domains that are not parallel and are rotated and they align with the direction of the field. Okay, then long answer question, give the properties of dia, para, ferromagnetic material. Okay, or this can be asked as compare dia, para and ferromagnetism. Okay, first of all, the magnetic materials are split up as three. Okay, one is dia, then para, then ferro. If the diamagnetic material is placed in a non-uniform magnetic field, okay, for that case let me see the behavior. If the diamagnetic material is placed in a non-magnetic field, it experiences a force. Due to that force, it will move from stronger part of the field to weaker part of the field. Okay, if suppose this is a diamagnetic material. Okay, I am placing a bar magnet nearby it. We know bar magnet having the magnetic field here. Okay, it is strong, but at a small distance it will be less. If suppose I move the magnet towards the diamagnetic material, this diamagnetic material will be repelled. That means it will move from stronger part of the field to weaker part of the field. Okay, then paramagnetic material, weak magnetism in the direction of the applied magnetic field. That means it will attract, it will move from weaker part to stronger part, but the magnetism is weak. That means it will attract with a small force, but a ferromagnetic material, it will attract strongly. Okay, then magnetic susceptibility, it having the negative value, but the para having negative and small, and ferro it is positive and large. Okay, then relative permeability, it is slightly less than unity, it is greater than 1, it is large. Then nature of the magnetic field lines. Okay, that means if the diamagnetic material is placed near a magnetic field, okay, that means a magnet, it will be repelled or expelled from the diamagnetic material. Okay, a diamagnetic material is placed in a magnetic field, it will repel the magnetic field. That's why it will repelled from the magnetic material. Okay, then paramagnetic material, it will attract slightly. Okay, but it will ferromagnetic material, it will strongly attract. Okay, temperature dependence of susceptibility. Temperature independent, diamagnetic material does not depend on temperature, but para inversely proportional to temperature, and ferro also inversely proportional to temperature. Let me see the example. Bismuth, copper, water are the example for diamagnetic material. Okay, if suppose the water is placed near a magnetic field, the water will be repelled. Okay, paramagnetic material example, aluminum, platinum and chromium. Okay, then ferromagnetic material, iron, nickel and cobalt. These are ferromagnetic material. Okay, then our next topic, hysteresis. Okay, very short answer question. What is meant by hysteresis? Okay, this is to answer this question you have to know lagging behind. Hysteresis means lagging behind, the phenomenon of lagging of magnetic induction behind the magnetizing field, that is known as hysteresis. Okay, you have to write this one also, lagging behind. For this you attain half marks. Then compare the properties of soft and hard ferromagnetic material. Okay, compare the properties of hard and soft ferromagnetic material. First let me see the properties. When external field is removed from the soft and hard, magnetization disappear. It will be gone. Okay, but it persists the magnetization. Area of the loop, the hysteresis loop is small, here it is large. Retentivity, for this it is low, it is high. Then coercivity, coercivity of soft ferromagnetic material is low and hard is high. Susceptibility and magnetic permeability, it is high, it is low. Then hysteresis loss, it is less, it is more. Uses, it is soft ferromagnetic materials that are used in solenoid core, transformer core, electromagnets. Okay, for making permanent magnet we can use hard ferromagnetic material. Okay, then example, soft iron, mu metal, stellite, etc. Here it is steel, alnico and lodestone. Okay, okay student, our class is completed. You have to make a notes for these questions. Okay, this is a today's homework. Okay, thank you.